Getting ready for those physics exams? Good, because we're about to tackle rotational dynamics. In just the next few minutes, we're going to break down all the core concepts you absolutely have to know. Okay, so here's our game plan. We're going to start with the real basics of circular motion. Then we'll get into the forces that are actually at play. After that, we'll see how this stuff applies to some classic exam problems. And finally, we'll wrap things up with the dynamics of vertical circles. All right, first things first. What does it actually mean when we say something is moving in a circle? I promise getting this foundation right is the key to, well, everything else we're about to cover.
So think about this for a second. What on earth could a spinning fan on your ceiling have in common with a planet orbiting the sun? It sounds a little weird, right? But the answer is the physics of circular motion. It's this incredible principle that governs just about everything, from tiny atoms all the way up to entire galaxies.
So at its most basic level, circular motion is, well, it's just an object moving along a circular path. I know, it sounds super simple, right? But that simple definition actually has a couple of really important implications we need to unpack. Okay, so here are the two big things you've got to remember. First, and this is a big one, an object in circular motion is always accelerating. Yeah, even if its speed is totally constant. You might be asking, how is that possible? Well, it's because its direction is constantly changing. And since velocity includes direction, the velocity is changing, which means acceleration. Second, the motion is periodic. It just means it repeats its path over and over again. Okay, so if we've established that an object in a circle is always accelerating, well, Newton's second law tells us that an acceleration has to be caused by a force, right? So there must be some kind of net force making it happen. Let's dive in and look at the forces that actually make things turn. Think about it. For something to turn, you need a force pulling it towards the center of that turn. We give that force a special name, centripetal force. This is the force that's constantly yanking the object inward, stopping it from just flying off in a straight line, which is what its inertia really wants it to do. Now, this is a point that trips up so many students, so listen up. The word centripetal is not a new fundamental force of nature like gravity or friction. It's not. The best way to think about it is as a job description. It's just the label we slap onto whatever force is doing the job of making something move in a circle. That job could be done by tension in a string, or gravity, or even the friction between your tires and the road. And then we have its famous counterpart, centrifugal force. You know that feeling, right? When you're in a car that takes a sharp turn and you feel like you're being pushed outwards? That's what we're talking about. But here's the trick. The key word is pseudo, or fake. It's not a real force. It's just the effect of your own inertia. Your body wants to keep going straight, but the car is turning under you, so it feels like you're being pushed out. All right, let's nail down the difference once and for all. Centripetal force, it's real, it's the cause of the circular motion, and it pulls inward. Centrifugal force, it's fake, a pseudo force. It's the effect of the circular motion, and it's felt as a push outward from inside the rotating system. Got it? Good. Okay, enough theory. Let's actually put this stuff into practice. We're going to walk through a couple of classic problems that, trust me, show up on exams all the time. First up, banked roads. You've definitely seen this, right? When you're on a highway or a racetrack, the curved parts of the road are tilted or banked. That's not just to make the ride smoother. It's actually some really clever physics. It's an engineering trick that uses part of the normal force to help the car make the turn safely, so you don't have to rely only on the friction from your tires, which can be super unpredictable. So how does it work? Well, the physics all comes down to breaking apart the normal force. Because the road is banked at an angle, the normal force from the road pushes on the car at an angle too. So we split it into two pieces, a vertical piece that perfectly balances the car's weight and a horizontal piece that points toward the center of the turn. And that horizontal piece, that's what provides our centripetal force. So we set up our two equations, divide one by the other, and boom, we can actually cancel out the mass and the normal force, which leaves us with a neat little formula for the perfect speed. And that brings us to the final formula. The really cool thing here is that the perfect speed has nothing to do with how heavy the car is. It only depends on the radius of the curve and the angle of the bank. Now, I'm telling you, this derivation is a total classic. You will see it on exams, so make sure you can walk through these steps on your own. All right, next up is another absolute classic, the conical pendulum. Now, this isn't your normal pendulum that swings back and forth. This one has a bob that moves in a perfect horizontal circle, and the string traces out the shape of a cone. Pretty cool. And you know what?
The way we solve this is almost exactly the same as the banked road problem. It's all about resolving forces. We take the tension in the string and split it into two parts, a vertical part that balances the bob's weight and a horizontal part that provides the centripetal force. Just like before, we set up two equations, we divide them, and we solve for what we want. In this case, the period of rotation.
And here's what we get. The final formula shows us that the time it takes for one full circle depends only on the length of the string and that angle. Again, this is a super important derivation. You really want to have this one in your back pocket for the exam.
Okay, for our last section, let's completely change things up. We've been talking about horizontal circles, right, where the speed can stay constant. But what happens when we go vertical? Think about a roller coaster loop. Now gravity is a huge part of the picture, and things get a lot more interesting.
So the single biggest difference with vertical circular motion is that the speed is not constant anymore. It just can't be. As the object moves up the loop, it slows down because it's fighting gravity, turning its kinetic energy into potential energy. And then, as it comes back down, it speeds up, turning that potential energy right back into kinetic. That roller coaster loop is the perfect example. And hey, here's a great example you've probably experienced. You know when you drive over a little humpback bridge? For that split second, your car is actually tracing the very top of a vertical circle. So let's break down the forces right at the highest point of that bridge. You've got your weight, mg, pulling you down, and you've got the normal force from the road, n, pushing you up. The net force pointing towards the center of the circle is your weight minus that upward normal force, and that net force is what provides the centripetal force. So, for that equation to balance, the normal force has to be less than your weight. And that's it. That's exactly why you get that light feeling in your stomach for a second as you go over the top. So what's the big idea here? It's that physics isn't just a bunch of formulas on a page. It actually explains the things we feel every day. That sensation of being crushed into your seat at the bottom of a roller coaster dip or feeling almost weightless at the very top, that's not magic. It's a direct result of the physics of vertical circular motion. All right, to wrap this all up, I've got one last question for you to chew on. Imagine a fighter pilot doing a full vertical loop. Where do they feel the heaviest? At the very top of the loop or the very bottom? And more importantly, why? Think about the forces, think about the direction they're pointing at each spot. If you can really nail down the answer to that, you are in fantastic shape for your exams. Good luck.